and review something that we had covered. Maybe I went over something a little too fast, particularly might be something on the computer where I did something and I hit a couple of buttons and all of a sudden something popped out and you're not sure what happened. This is always an opportunity then for you to go back and check out what it was that we did. Okay, and so our before I get started with describing the timetable and the basic philosophy of the class, does anybody have any early questions? You can all hear me okay?
Actually, I kind of did.
Okay,
Yes, I can hear
sure.
you.
Do you, oh, go ahead. Here, okay. I wanted to know if I should take the astronomy class in conjunction with this.
It never hurts to have more astronomy, but I'm going to be spending the first 6 weeks of this class giving you an overview in the aspects of astronomy that you'll need. And so it's not required, and I'm not going to say it's not needed. People sometimes ask me in physics, I teach physics also, whether or not it's important to have math. And I say, well, yeah, the more math you have, the better. And so here too, the more astronomy you have, the deeper your understanding would be. But I am going to be spending more time on the theory than was previously done when this class was originally taught in 2018. And that class was very successful at getting people published. But I do feel like a little more time is needed than was given in that course to get you up to speed on the basics. And so I'm not going to cover every aspect of astronomy, but I will cover the things that I believe are important for this particular research project that we're doing.
Also, I know that there's an astronomy club that meets out in Santa Margarita a lot, and I was wondering if that's something that the class would be doing or could be doing, because I actually have a large area out in that area that could host. So, if that is an option.
Well, that is a very nice offer. What we're going to be doing in this class doesn't even require looking through a telescope. We are going to be first searching through databases to find legitimate candidates for analysis for a double star system. And so that is our key goal is to analyze what are called binary star systems. And so a binary star system is one that has two stars orbiting around each other. So, of course, we're in a single star system in the solar system, but at least half of the stars, we believe, in our galaxy, and maybe more than half, are members of either double, triple, or quadruple star systems. And so they have stars orbiting around each other rather than just a bunch of planets going around one star. And so this is an interesting kind of solar system to look at because there's so many of them, and also because the orbits of planets that might be habitable might be compromised by the gravitational forces that are associated with having two fluctuating masses. And then which star does the planet orbit around, or does it go in a figure eight? That's going to be extremely unstable. And so it's quite possible that we might be able to find places once we understand better what's going on with the binary star systems where life might be able to exist in a completely different kind of a system. Like when on Star Wars they had I don't know if you saw Luke Skywalker. We looked up at Tatooine at the double stars system. There could be something like that, but the stability of the orbits is something that we're not real clear about. And so we're going to be focusing our attention on that. And once we've identified stars that can be photographed, we are going to put in an order to a worldwide array of telescopes that are robotic telescopes. And so the telescopes will take the pictures for us. And so we're going to be looking then for a, uh, a star system that, let me just bring the whiteboard up here if I can find the pen. Hmm. Okay. Never mind. I lost the pen. Oh, here it is. Okay. Okay. So just go back where we were there. Whiteboard. So we have essentially then, can you all see this okay? Can you see what I'm writing on the virtual whiteboard? Is that good? Okay, so we then have stars that are binary stars are ones that would orbit around each other in this kind of a fashion. And so they're not exactly orbiting around each other, but each one of them is orbiting around a common center of mass. We can think of that center of mass as being the balance point between these two stars. And so by being able to determine the orbit of one of these stars around the other, we can then determine whether or not we actually have a binary star. And so our goal then is to find a suitable binary pair. And by suitable here, I mean that it needs to have similar brightnesses to the stars so that one star doesn't dwarf the other. And so we'll look at what the magnitude scale is all about, but this means that the difference in magnitude will be less than about 4. So that we don't have one star that's, say, 10,000 times brighter than the other. So that when we do the photograph, we'll be able to see both of the stars together. And so when we say a suitable binary pair, then the brightnesses have to be similar. And also the magnitudes should be bright enough. So now, even though we have a difference in magnitude, so that the differences in the brightnesses of the star are fairly close to each other, we also have to have magnitudes that are bright enough for us to be able to see. Other things that we're looking for are the proximity of the stars to each other. The stars have to, in terms of their angular distance, they need to be fairly close together, but not too close. They have to be just the right distance apart from each other. Now, what happens if they're too close? Well, if they're too close, then we take the photograph, then our robotic telescope is not going to be able to resolve one as being separate from the other. So you go, okay, but what if they're too far away? Well, if they're too far away, and this is something that we'll talk about a little bit more later, but Kepler's third law tells us that the farther apart the stars are, the longer they take to go around each other. And so even though the two stars are going around each other, if we focus in on the brighter of the two stars, that's what we call the primary star. So that's the brighter of the two. If we make that the center of our coordinate system, then the secondary star, with respect to the primary star, will describe an elliptical or kind of a squash circle orbit. So here's our secondary star, here's our primary star. And so then our goal is to find a star that's been studied before. So that's another thing that we're looking for. It's got to be studied before so we can compare it, what we find, to what's happened in the past. And so preferably, we're going to be looking for uh, um, something with at least 100 years worth of data. So in other words, we'll be finding data points on this elliptical orbit that are many, many, many decades old. And in some cases, we'll be looking at maybe the first time it was discovered might be, for example, 1897. You know, that might be it. And then as we move along the orbital path, eventually we'll get to, say, 2015. So we want something that's been studied before, but not too recently. Because if it was studied, say, in 2023, then that data point and our data point are going to be right on top of each other, and we're not really contributing anything. It's not particularly publishable. Okay, and so we want something where the brightnesses are fairly similar to each other. We want something that's been studied before. We want the absolute brightnesses to be bright enough so that they'll show up on the as a picture on the robotic telescope. But we don't want them to be too far apart. If they're too far apart, then the picture is fine. You know, that if it's too close, then we can't resolve them as separate. But if they're too far apart, we have another problem. That means the period is too long. So the period is the amount of time that it takes for the stars to orbit around each other. But if they're far apart, and this is something we'll review as we get to Kepler's laws of planetary motion, but the farther apart the stars are, the longer it takes for them to move around each other. And so for more than about 5 arc seconds, then the period gets to be, say, 4, 5, 600 years. And so we can study a star like that, but if the period is 4, 5, or 600 years, all of the data points are going to be smashed down and will hardly make up any of the orbit at all, even if we've gone back 100 years. And so it's going to be difficult for, and so once we find this pattern, and so we need something where we can actually get a little bit of an arc going to it, so that we can maybe fit an ellipse into it. Uh, but in order to do that with the telescopes that we have available to us, we've got a fairly rigid set of constraints that have to be satisfied in order for our star pair to be a good candidate for study and finally for publication. And but fortunately, we have a huge data set. Gaia has brought in something like a few billion data points of different stars. And so one of the main purposes of that mission was to find planets around stars. But in order to have enough information to find planets that are orbiting around stars, you have all kinds of extra information available regarding stars that are going around other stars. And those are much easier to analyze. And a lot of that data is just not being utilized. And so we're taking advantage of the fact that there's a gigantic wealth of data that is associated with this Gaia project, which need so much data because their constraints for trying to find planets around stars are much more challenging than our constraints of just trying to find the right kind of stars that go around stars. And so this is then um, our task then in the beginning is to go through and from a few billion uh, possible candidates, narrow it down maybe to I don't know, 100 or 200. And then start going through those. We'll have certain search characteristics that we'll be looking for, and then you'll get a few candidate stars. And then we'll look at those and see whether or not one of them is better for study than another. And so once we find the star, we find a good star, then we are going to be interested in finding out whether it's a physical or an optical binary. Now, optical means that it's a phony binary star system. Optical just means that you have two coincidental stars that look like they're close to each other, but one is actually probably much farther away than the other one is, and they just happen to be lined up. And so if we find this kind of a pair and the previous studies look like this, and then our data point looks like that, and it continues on in a straight line, then that's an indication that this is just a coincidental alignment of these stars and that it's not actually two stars that are physically bound. And so we can tell that by looking at the path that's taken by all of the different data points that have been accumulated for uh, that candidate binary star system. And if it looks like it's going off in a straight line, then that would tell us that it's an optical or a phony binary. So does that mean that everything's wasted and that all of your work is down the drain? No, we are interested in identifying which uh, which pairs are real and which pairs are not real. And so that's still considered publishable data if we can verify that we have a an optical binary. But if in fact we can get and start finding a pattern, and it looks like it goes in some kind of an arc like this, then that looks like something where we might actually be able to fit that and extrapolate into a binary orbit. And so we may not be able to make that conclusion. It's not necessary to make that conclusion, but it is something that would be fun to do. And so there are other things we can do as well. Once we've selected the star, then the next part of the process then is to place an order for a photograph. Are there any questions so far? Okay, well, let me just get out of here then and share my screen.
I did have a question, but you answered it. I was asking, so if there's an arc, does that mean it's a binary?
It is a good indication that it's a binary. There are other things to look at, though. Let me just, before to answer that question, let me just back up here. Just keep doing here? Connection error. Cancel. Okay, never mind. I'm sorry, what was that question again? I'm getting uh, distracted by all of these computer problems.
I was asking, so if it's in a straight line, obviously it's not binary. But if there's an arc or, a curvature to it, that means it's good likelihood to be a binary.
It's a good possibility. And then once you have uh, you found that the data is suggestive, then you can take the next step and look at the distances of the stars. And so let's say, and so you can go to another program that locates uh, what's been going on with this binary star pair, and you can see what are the distances. And so typically the distances are given in light years. So this might be 75 light years away, and this distance here might be 52. So even if they're in a nice arc path, that and it looks like we might be able to do something with it. This kind of information would tell us that they're probably not gravitationally bound because they're too far apart from each other. There's also other information we can get from Gaia, like how many arc seconds per year does it move in the horizontal direction and in the vertical direction. And so the stars are going to move. And if they're both moving at the same rate and they're both at similar distances, those are the things that we might be able to use then uh, to really tie it down and say, well, yeah, it looks like we can uh, close the lid on this thing, and we've got a binary system in our and that we've proven that it is in fact a binary star system. Now, one other thing before I get back to what I was about to show you is that um, uh, these uh, um, these stars that we're looking at m- uh, in terms of the overall orbit, if they're a little bit too far apart, then some of the data points may uh, be very, very close to each other. But this doesn't mean that all of the data that was taken in the past was good data. And so essentially, then what we are going to do once we have our candidate uh, binary star pair to analyze is that we're going to take pictures of it. Okay, and so here what I've done is I've gone to the home page, and so this is something you can do too, either now or later when you feel comfortable doing that. Uh, and what what we can do here is there's a couple of things I wanted to point out to you. One of them is that this link, where it says links to programs and videos used in the class, can be very useful. So I'm going to click on that, and this brings us to this is basically uh, the course that I took in getting ready to teach this class. Um, Russ Genet was the originator of this class and developed it back in the around 2016 or so. And so he set up a lot of this stuff and he wrote his own star handbook. But notice that if you go to that link that I pointed out, and I also put this on the instructions, the previous announcements that I gave you, is that you don't need the Star Handbook because you can just go to this link and then just click on Star Handbook. And, Russ wanted to get some income for his book, but it's right here. So there's no reason for you to have to buy it. And so then you can just click there and you've got the whole handbook is there online for you. And so that's all good. So you can do that. And um, here is a nice little link on writing proposals. So that's on this first page. On the second page, this would be the journal that you would be publishing your uh, your results in, the Journal of Double Star Observations. And so here is a link to that so that you can see what kinds of papers are on that journal. And so this would just kind of give you a feeling that this one here uh, is a very important one. This was done by three of my students from last semester. And so this one by Ken Dostek, uh, Ave, and Amelia. And so you can bring this one up, and it gives you a pretty good template for what's been done in the past, what's worked, what hasn't worked. And We can go down a little farther here. This is the LCO array, so Las Cumbres Observatory. And so even though I'm not going to get to the stuff quite yet, this is stuff that you can be going through and checking out and just getting more familiar with some of these ideas. But here is the robotic telescope array. And so these are telescopes. And I'll talk more about how telescopes are constructed. But these are what are called reflecting telescopes. They use a curved parabolic mirror, and they have an aperture size, or the size of the hole that lets the light through, is around 1 meter, sometimes more. And so it's good to be able to let a lot of light through. And so notice that we've got these different uh, places in the world where the LCO array exists. And so we're going to have to find a star not only that satisfies the right criteria, but also one that is visible at this time of the year so that it can be photographed. And so the LCO array then would choose the first available telescope that has a good view of that part of the sky. Uh, and then if one picture looks pretty good, then you go, well, what the heck? Let's take 10 pictures. So we'll take 10 pictures, then we'll go back. A little better at moving around here now. And you'll, for some reason, it's not always doing what I want it to do. So you set up a table of information. And so what you'll have then are two essential pieces of information. This is your primary star. This is your secondary star. And so there's two things that we're going to want to determine. This direction here is north. This is south. This is east. This is west. So we're going to want, with respect to this north, and it's a funny way of writing it, but it's their standard way of writing it. We're going to want our theta value. Okay, so theta then is measured around like this to this point. And so this would be our theta here. So we want our theta and we want our rho, and that's our angular distance between them. So we have rho and theta. We have 10 different pictures, and so hopefully they'll all be somewhat similar in their rho and theta values. So you have 10 of those data points. You'll average those and find the standard deviation. So we want them to agree fairly much with each other, but there can be problems with the viewing conditions. There might be a little bit of smoke in the air, which we've been seeing a lot of lately, or there could be clouds, or there could be some kind of atmospheric disturbances that create little ripples uh, in the paths that the light takes. And so by taking 10 pictures, and then we'll put each one of these pictures into a another computer. So we make an order with the computer, we get the computer files back, and then we load that file into another file, which then uh, calculates the rho and the theta values for us. We do 10 of those, provided that all 10 data points are good. Then we can do standard deviation, which is just an indication of how much the the different data points are fluctuating from each other. And as long as the standard deviation is low, and the results that we get are somewhat consistent with what has been observed before, then we can plot our data. And so then in our final step, we'll go to the Gaia program. We'll see whether or not these stars are at similar distances away, how fast are they moving across the sky, and do those kinds of things match up, plot our point, and then write up the paper. And so that's kind of it in a nutshell in terms of uh, what our goals are. So my first objective is to get you feeling comfortable with all of the different processes that are taking place in the analysis, and feel comfortable with how the telescopes work, uh, how you view the sky, how the sky moves, how you measure things in the sky uh, using celestial coordinate systems. And um, and then uh, there'll be a place for you to tell me what your level of interest is, what your expertise is, and if you have people that you want to work with already, but then I'll take that information and try to put together the best teams that I can. And then we'll start selecting the star and go through each one of those processes. There any questions about that? Sound reasonable? Sound like it's doable? Okay. Let me just point a couple things out to you then. Go back to, okay, so this was our LCO array. Let me just go back to, okay, this was our, um, go back one more. No, not that's too far. Go back to here. Okay, so here we have, this is just our home page. And so we talked a little bit about things that you can kind of look ahead to here. Uh, you can find the Star Handbook. We can go through and let's just look at a couple more of these things. This is a picture of one of those robotic telescopes. So they're kind of cool. Uh, Here, this shows the coordinate system. So this is something you can look at in a little more detail. But this is what we're basically looking for. And it's a funny way to write it. But with the primary star in the center and north down, then we measure the angle around from east to south to west that way. And so if we're going from north toward east, then that angle there would be like 10 degrees. But if we went from north to south, that'd be 180. We went to southwest, then that would be like maybe uh, 235 or something. And then this would be 270, and then 360 would be zero. Okay. And so here then is an example of a double star system right here. And so you see then that this primary star is much bigger than the secondary star. They're far enough apart so that the primary star isn't completely swamping out, and so we lose resolution with the secondary star, but it's not so far away that the period of the orbit would cause all of the data points to plot over each other. So here would be the kind of a plot that we could do. And so these would be previous data points. And so you notice that there's a lot of scatter here in some of the previous data. And so that means that, maybe they didn't have as good of analysis techniques back in 1920 as they do now. But we're trying to work with uh, get as far back as possible so we can get as far along the elliptical orbit. And one thing that could look kind of cool in your paper would be just some kind of a brief uh, summary of the first observation that was made. If that information is available, you could talk about when it was discovered and when the first data point came in. And then this would be your data point, and then maybe there's a little bit of a scatter in data here. And then here again, this would be another set of uh, plots. And so this is color coded in terms of more ancient versus more modern plots, but you would make sure that you would want to have your plot as a different color from the other ones that were done previously so we could distinguish your contribution to the other ones. And let's see, go down here a little farther. Some of this stuff is just kind of getting a little farther along the line than we need to be right now, but you can go as far along in this process of looking at things as you want. Eventually, we'll send out to the U.S. Naval Observatory for all of the previous data that's been gathered on that binary star, and that'll be part of your paper. And Afterglow is one of the programs that we use to analyze the rho and the theta. And then see here. So these are just things you can look at that illustrate some of these things if you want to look ahead. But that's not required right now. There's some more advanced information, and then eventually, somewhere down here, there's a computer program that can give you a feeling called Stellarium, can give you a feeling for how the sky works. And so I think that's something that if I don't see that real soon here, I'll find that for you next week and I'll show you where that is. But if you can find Stellarium in here, then oh, here. No, that's not it. Okay, so I'll find that for you later. Now, in your on your home page, you'll have different units, and each unit has a specific set of goals in mind. The way that I've constructed Unit 1 is basically to get you started, get you used to some of the basic ideas that we are going to be using in just kind of general astronomical analysis. And so if you go to Unit 1, I put a lot of things together here for you. Here would be your Unit 1 overview. And then down here, here's your reading assignment. Here, Chapter 1. Then you would watch this video and take Quiz 1. Okay, and so for next week, what I'd like you to do is to go through, read through this chapter, the video, and take quiz 1. And then I've and that would be due by next Friday. The um, quiz two would be this reading assignment here, and then you'd watch this video and take quiz two. Now you can take the quiz two times, and it's not a complicated thing. If you've read through the sections, you should be able to get 100% on it. But if you take it a second time, it'll average your two quiz scores. And so quiz two and quiz three would be due by 2 weeks from today. And then I'll start in on the some of the introductory material that is essential for having a good basic understanding of the principles of astronomy that will be necessary to make sense out of the data. And so as we go down here, this would be something that might be uh, interesting for you to look at next time. It's a little video. I think this is a YouTube video on angular measurements. So how do we measure angle? And then this talks a little bit about the celestial sphere and declination, right ascension. So those are all things that I'm going to be going through in my lecture next week. But just to give you a little bit of a preview of that, um, the sky we can think of as broken up into kind of a grid that's similar to the kind of grid that we see with longitude and latitude lines on the Earth. And so these would be our latitude lines, and these lines that go down this way would be our longitude. Okay, so here in San Luis Obispo, we're at about 35 degrees north latitude, and our longitude is 120 something, I think. And so we're probably somewhat comfortable with this idea as we go across this way from right to left. That is pretty much an east-west motion. And if we go vertically like this, it's pretty much a north-south motion. Uh, Now, the celestial grid is similar, but just imagine that now we've got a big sphere surrounding the Earth that's got this same grid pattern on it. And so you're standing here, and uh, if you look straight up, that would be on this diagram here. That would be that would be tangent to the Earth's surface. That'd be looking toward the north. If we look this way, straight up, away from the equator, then that would be looking out essentially in the radial direction. So if we look straight out and then up like this, so in other words, if I'm standing here on the Earth's surface and I look up like that, up toward vertical, that's like here looking straight up and then looking vertical uh, toward true north. And that direction then, that angle of sweeping up, which is like latitude, but it's latitude on a grid or a spherical grid that is above the Earth's surface. That would be equivalent to what we call declination. Okay, so the analogy of latitude on the Earth's surface could be thought of as being, okay, if I look straight out from the equator and then I look up toward the north, or like straight up from the horizon type of thing, up toward the north, that would be like declination. It's not exactly the same thing as that, but it's similar to it. And then if you look from east to west, that's like this kind of a direction. And so that's called right ascension. We have right ascension, which goes this way. We have declination, which goes up this way. And so all of the stars then have coordinates in terms of what their kind of east-west right ascension direction is, and kind of the up to uh, straight overhead north type of thing, which would be your declination. And so you can get used to the basic ideas of the coordinate systems. We'll be looking at things next week like angular measurement. You have degrees, 60 seconds, 60, sorry, minutes in a degree, and then 60 seconds in a minute. So a lot of times we'll be looking at what are called arc seconds. So an arc second is 1 over 60 times 60, or 1/3600th of a degree. So a lot of times when we measure angles then, either right left, right ascension, or north south, in terms of uh, differences between, say, one binary star pair and the other, we would be doing it in arc seconds, which would just be measuring essentially an angular distance that is on the order of maybe a few thousandths of a degree. So it's not a big angular shift. Okay, and so that is just kind of a brief overview. I'll have a lot more time to talk about this, and like to give you a chance to do a little bit of the reading, take a look at some of those first videos from Unit 1. And then if you have any questions about the quiz, I'm not going to make the quiz be due until a week from tomorrow, so that you can check with me if you're having any questions. But if you are feeling comfortable with this and want to work ahead, I I have the first 6 quizzes available and all of the introductory information, and so you're welcome to work ahead. And if anyone is, got already a real good understanding of astronomy and really wants to blast through, I can point you in the right direction for getting into the project sooner. Okay, so that I think is probably good enough for our first uh, first lecture. So let's just see what kinds of questions we have regarding any of this. Is it clear so far what it is that we're trying to do? Anything that I can clarify for you, or any questions I can answer that would be helpful?
I have a quick question. I don't know if you went over it briefly and I missed it, but are all of the quizzes going to be like, are they all posted in Canvas with their due date on like the calendar, or do we have to go find
Yeah,
them and
you
do
can
them
check
on our
on
own
the
time?
calendar
Okay.
that's on the syllabus page, and um, it's all posted. And
Okay.
so I've tried to make it kind of an easy schedule so that you don't have to jump right into it. You can get used to, if any of this seems unfamiliar to you, you can um, it gives you plenty of chances to ask questions and stuff. But if you want to work a little faster, and if I see that everybody's going faster through this, and you want to get started with the actual data analysis quicker, I can ramp this part of it up so that there's more time to do the paper. So I can be
Thank you.
flexible with how I just I don't want you to get into something and then just start going through the motions without really understanding what it is that you're doing. And so I want you to have enough information so that you feel comfortable with each of the different concepts that we're going to be looking at. Any other questions?
I have a question.
Sure.
Um, you showed that PDF book earlier in the
Right.
uh, meeting. Is that's the textbook we're
That's
using?
the textbook. Yeah. Yeah, so again,
Okay.
for that, you would, I think the easiest way to find that is to just, let's see here. This is unit one. Go back to home. It's pretty sluggish right now. Oh, there it is. Okay. Go back to home, and then you can just click on this thing that says Sam at the end. That's the link to programs and videos used in the class. And so that just has kind of a nice array of things that it's just kind of for fun to check out, to fill out your knowledge of different aspects of the course. If you just click on that, then that gives you the link directly to the STAR handbook. Now, a lot of the assignments are keyed in so that if you went through Unit 1 and you just click on the reading assignment, it'll just take you to that part of the book. So like in Unit 1, go back here. Now I'm going to go back to Unit 1. See here, we've got chapter 1.pdf. This is the reading assignment. If you clicked on that, it takes you right to chapter 1. And then you'd watch it. So you do that reading, watch that video, and then you're ready to go. You're ready to take quiz one. And then if you say, all right, that was pretty easy, let's do quiz two. So then you do this reading assignment here and there, watch the video, and then take quiz two. And then if you mess it up, take it again, and the two scores will be averaged. Does that look like it'll work for you?
Yep, looks good.
Right. And if you have questions uh, that suddenly come up, and you are welcome to email me, and we could set up a time when I could talk to you on Zoom, or you could come by one of my office hours at Cuesta, the main campus, and I'm there a lot. I'm in room 2310. It's in the 2300 building, Monday and Wednesday from 11:15 to 12:30. And on Wednesday, I'm in room 2609 from, let's see, 2:30 to 3. On Thursday, I'm also in room 2. This is not working very well. 2609, from 12 to 12:30. And so these are immediately following my classes. I have office half hours from 2:30 to 3 on Wednesday, and Thursday 12 to 12:30. On Friday, 9 to 9:30 in the physics lab. So that's 2301. No, I'm sorry. That's 2101 is the physics lab. So those are times when I can talk to you directly, or you could email me, and I'm happy to set up a time to talk to you on Zoom. And so those are my contact hours, and feel free to just swing by. This is in my regular office is um, a good long office hour, and so those are all options for you in terms of contact. Any other questions? All right. Well, thanks for coming, and I'll if I don't hear from you, I'll see you again next week.
Thank you, Professor.
Thank you.